Welcome back, Physical Science 20. This is the second video in the section 4.6 double displacement reactions. So we looked at this one here, looking at the precipitate chart, seeing which combination will make it precipitate and which will not. So here we'll look at another example, potassium sulfate and iron 3 chloride. So here we look at, and we know it's iron 3 chloride because chloride is -1, and since we need 3 of them to balance 1 iron, it must be iron 3. So taking a look here, of course potassium combined with chloride could be a possibility, or iron 3 combined with sulfate. And of course you see the compound here, iron 3 sulfate, forms this because we have +3, -2, lowest common multiple of 6. So if I have 2 of those 3 positives, I get 6 positive. If I have 3 of the 2 negatives, I get 6 negative. So Fe2SO4 all to the 3 is the formula there. But first let's look at this, potassium chloride. Potassium chloride. Chloride with potassium. So potassium is not on this list. It must be over here. And of course that means aqueous. It is soluble. Potassium and chloride are soluble together. So that's not a precipitate. Iron 3 sulfate. So let's look over here. Iron 3 sulfate. So sulfate and no iron there. So iron must be on this side. Aqueous again. So in this case, no precipitate. So you can see how I did that. I looked to see if there was a possibility of a precipitate first, and then if there wasn't, I looked at the other combination. So this one, no reaction, because no precipitate forms. Okay, so take a look at these ones. Which of the following combinations results in the formation of a precipitate? Write the balanced chemical equation if it does. And make sure you include the states, which is the solid, which is the aqueous. Okay, so you may wish to pause the video and try those 3 questions. Okay, if you had a chance to do the questions, let's look at A, sodium sulfide and lead 2 nitrate. So sodium nitrate. Now one thing should joggle your memory about nitrates. Nitrates are soluble in everything. So the nitrate is not the precipitate. What about lead sulfide? And it's lead 2. Because here we can see we have 2 nitrates balancing it out. So that it must be lead 2. Lead 2 and sulfide. Let's take a look. Sulfide will form a precipitate with anything on this side. Is lead on that side? Could be. Because yes, it's not, lead is not a group 1 element, and it's not a group 2 element, and it's not ammonium, so lead is on this side, so it is a precipitate. So there we have it. Lead. Now again, what you may wish to do is write down the charges just over here. Sodium is Na+, sulfide is S2-, lead 2 is Pb2+, NO3 is NO3-, and then interchange partners. Okay, so you may wish to do that. It's a heck of a lot easier than just simply trying to look at it like this. So lead 2 positive, 2 negative, PBS. Not the TV station, but the compound. And sodium is Na+, NO3 is -1, so they come together 1 to 1 as well. To balance it though, we can see that I have 2 nitrates over here, so I need to have a 2 in front of here to get my 2 nitrates. That gives me 2 sodiums, and lo and behold, I did have 2 sodiums with the sodium sulfide. Okay, next question. Iron chloride. Since I have 3 chlorides here, we know chloride is -1, so if I need 3 of them to balance 1 iron, that iron has to be iron 3. And sodium carbonate. Carbonate is 2 negative, sodium's 1 positive, so that's why I need 2 sodiums here. So looking at the combinations, sodium chloride. Switching partners here. Is sodium chloride a precipitate? You know without even looking at the chart that it isn't, because sodium chloride, you know that dissolves in water. Chloride, yeah, sodium's not on the precipitate part, so it is AQ. Looking at iron carbonate. iron 3 with carbonate. Let's look at that. Carbonate, iron 3, is it a group 1? No, iron 3 is not a group 1, and it's not ammonium, so iron 3 exists on this side of the chart. PPT, it's a precipitate, it's a solid. So I actually jumped down to C and did that one first. Darn it, I didn't do B. So, setting that together, sodium chloride, Na+, Cl-, they come together in a 1-to-1 ratio, NaCl. Don't fall in the trap of writing down Na2Cl3. The reason why I have this 2 here is that's how sodium needs to be combined with carbonate. Chloride needs to have 3 to combine with iron 3, so don't fall into that trap. Look at the original. Look at the original charges. Sodium is +1. Chloride is -1. So use those charges, because I see that mistake being made time and time again. Iron 3 and carbonate. Iron is 3+, carbonate's 2-, lowest common multiple is 6. So if each iron is worth 3, I need 2 of them to make 6 positives. If each carbonate is 2 negative, I need 3 of them to make -6. So Fe2CO3 taken 3 times, that's the formula. And of course, to balance that out, 3 carbonates, I've got to put a 3 in front of here to make 3 carbonates. That's going to give me 6 sodiums. So I need a 6 over here. That gives me 6 chlorides. So I need to put a 2 here. 2 times 3 is 6. 2 irons, 2 irons. Okay? And son of a gun, I gave you the answer for B. Let's take a look at why that is so. Let's look at the opposite partners. Ammonium sulfate. Sulfate with ammonium. Sulfate, ammonium is not in this list, so it must be here. Aqueous. All right, so that one is not a precipitate. Potassium chloride is the other possibility. Potassium chloride. Chloride, potassium is not on this list, therefore it's over here, aqueous. So no reaction there. Okay, so just using that precipitate chart to see if certain combinations make a precipitate. If they do, that's a reaction. So as I mentioned, double displacement reactions. It could, the first type here, we're to go way back here. So precipitate formation. Second way they could happen is by releasing a gas. And third way, becoming a neutral substance, an acid-base neutralization. So let's look at the gas formation one now. Reactions that produce a gas. Double displacement reactions involving acids can produce a gas. So highlight that, acids. This can occur in 2 ways. First, gases may be produced directly. For example, the addition of an acid to a sulfide compound. Highlight that. A specific kind. Hydrochloric acid and to something that's a sulfide. For example, potassium sulfide. We get a double displacement reaction. So we get hydrosulfuric acid, H2S. Sulfide is actually 2 negative on the chart. If you look over here, sulfide 2 negative, hydrogen's 1 plus, so it's H2S. And then of course the other combination here, potassium combined with chloride, +1 -1 KCl. So we get H2S gas, sometimes referred to as hydrogen sulfide or hydrosulfuric acid. This toxic gas has a distinctive odor of rotten eggs. Spilling an acid onto a sulfide compound releases this toxic hydrogen sulfide fume. For this reason, the use of sulfide has been banned in quite a few places. Gases can also be, so there's the one reaction, put a star beside it. The one gas, hydrogen sulfide, when you have a sulfide compound combining with an acid. Second one, carbonates. Gases can also be produced when an unstable product of a double displacement reaction decomposes. For example, the pattern of double displacement reactions suggests that magnesium carbonate, make sure you highlight the carbonate, just like over here, sulfides, here we have carbonates. When they combine with an acid, such as sulfuric acid, so first of all, we get MgSO4. The negative part of the acid and the positive part of the compound, the carbonate, magnesium sulfate, and the H and the CO3, carbonic acid. Now, carbonic acid is unstable and it readily breaks down. It's actually a little decomposition reaction here, breaking down into water and carbon dioxide gas. So quite often here we'll just, instead of writing down the two separate reactions, simply write the carbonate combined with an acid makes the compound that has the negative part of the acid and the positive part of the carbonate combined with water and carbon dioxide. So highlight that part. That gives you a hint there. Okay, I think I'll stop the video there and we'll look at the final part in part 3 of this 4.6 section. Okay, we'll see you soon.